Hello, my name is Junior Carvalho, and today I'll be going through my answers to the 2021 AP Physics C Electricity and Magnetism FRQs. This was released the day that I'm recording this, May 5th, and this was the actual FRQs that were given out 2 days ago during the first administration on May 3rd. And since I'm a student of AP Physics C Electricity and Magnetism, I took this exam myself. So I'll be going through, what the answers should be, I would hope. Unfortunately, unlike my previous videos where they actually give out the scoring guidelines for the multiple choice, they haven't released those yet for these FRQs, and so I'll be taking my best guess at what these answers are, and hopefully by showing you my reasoning and my logic, hopefully they make sense. To me, they make sense. But if you think that I'm wrong, if you think that some of my answers are maybe incorrect or my explanation wasn't really that good, please let me know in the comments, and I'll try to leave some sort of correction description. But yeah, please enjoy the video. So the first FRQ was a circuit problem, and I remember when I opened my exam and I saw this giant monstrosity, I was really scared because I thought it was going to be a multi-battery sort of circuit that sometimes we deal with. But fortunately for us, it was only a single battery. It was just a lot of resistors and a lot of capacitors that we had to deal with. So let me read out here the question. The circuit shown above is composed of an ideal 10-volt battery, 3 resistors and 3 capacitors with the values shown, and an open switch S. The capacitors are initially uncharged, and switch S is now closed. So part A asks us calculate the current through R1 immediately after switch S is closed. And so we're being asked about the current through R1, and so that's going to be IR1 at time 0. And something that about circuits that you should memorize is that for time 0, well, if the capacitor is initially uncharged, so any capacitor that's initially in charge, which they all are, given that voltage is given by Q over C, then the voltage of the capacitors at this point will be 0. So that means that the voltage across here is 0, the voltages across here is 0, and since these are all in parallel, the voltage across here is 0, and the voltage across here is also 0. So all of this is basically, you can kind of ignore. And since the voltage across here must be 0, right? Let's write this like this. IR2, or voltage of R2 is going to be 0, and given that voltage for resistors is given by I times R, well, the resistance cannot change, but the current can. That's to say that the current through R2 and then also R3 is going to be 0 as well. So what you can imagine is happening here is that there's a current going through here, and then it probably passes through here. It might also be passing through here, given that there's no voltage drop either way. But anyways, the only resistor that current is actually passing through is R1, and so that vastly simplifies our answer here. And so we're going to be using here Kirchhoff's rules, which is looking at the voltage drops across the circuit. And so I'd start here with the 10-volt battery. And as we go across, we subtract out I1 times R1. And then, well, are we subtracting out anything else? No, because we just said here that the voltage across all of this is going to be 0. And so we can already say that this is equal to 0. And we go basically in a loop like so. And then this is actually pretty simple then. I1 is just going to be 10 volts over R1, which is in this case 100. And so then you will get that I1 at time 0 is going to be given by 0.1 amps. Part B, we're told that the switch S has now been closed for a long time and the circuit has reached a steady state, which is really to say that time went on towards infinity is the way that I like to think about it. And we're asked to calculate the potential difference across R1. So now we're being asked about V of R1. So as time goes off to infinity, what happens to these capacitors? Because that's really the changing part of the circuit. Before we said that at time 0, the voltage across the capacitor was 0. Now when time goes off to infinity, the voltage is going to be, well, basically high enough so that there's going to be no current going through the capacitors, okay? So now I would note this like this, that I sub C is going to be equal to 0. There is no current passing through these capacitors here. And so that means that they're all passing through here instead, okay? So what I would do here is we have to calculate for R1. Well, let's figure out what the equivalent resistance of all of this would be. Calculate the amps of the current, and that should be the current that goes through this R1, given that this is going to be in series with whatever this is. So let's actually get to doing that. So let's calculate what the equivalent resistance of these two are, and I'm going to note that by R2, 3. And given that these are in parallel, I have to use this formula here, which is from your formula sheet. Oh, that should be a 2, and this should be a 3. And so we're doing 1 over 30 plus 1 over 60, and then we put that in a calculator, and then we invert that. And what we'll get is that R2 comma 3 is going to be given by 20 ohms. Okay, and then you can sort of imagine I now have a 20 ohm resistor that's just passing through one thing like this, and then I have to find the overall equivalent resistance, which is going to be R sub EQ here. I'm going to add R1 plus R2 comma 3. Okay, and so then I'd be doing 100 plus 20, and what I'd get is 120 ohms, like so. Okay, and so now if I want to find the current through R1, which is really just going to be the same as the current through the battery here, since they are in series, I can do, again, Kirchhoff's rules here, and it'd be something like this, and let's just call this REQ. Also, actually, we could just call this I1, since that's the current through the first resistor. And this is going to be the equivalent resistor, and this is equal to 0. And so again, the way I'm getting this is by just imagining it's a simple circuit that has a battery, and then a resistor, and then it connects back, and this is the REQ. This is 10 volts. That will lead me to figure out that I1 is going to be 10 over REQ, which is 10 over 120. And then if I put this in my calculator, what I'm going to get is that the amps of that is going to be, or actually let me say I1 is going to be 8.083, I believe. Let me confirm that. Yes, and this is going to be repeating like so. And now I basically go back, and if I want to find the voltage across the first resistor, so voltage across 1 is going to be given by I1 times R1, which is to say, we could put this as a fraction actually, 1 over 12, which I got from here, right, times the resistance of R1, which is going to be 100, and again, using these decimals here, I'll be able to see that V1 is going to be 8.33 volts. And so that would be our answer. Part C and part 1 of part C, we're told to calculate the charge stored on the positive plate of capacitor C2. That's this right here. And this is going to be a little bit of a tough problem, a little bit involved, but let's take this step by step. So to get charge of, or Q2 here, charge of capacitor 2, it'd be given by this formula right here, okay? But these are a lot of unknowns because we don't know this and we don't know this. That's going to be maybe be the, or sorry, we do know the capacitance, but we don't know the voltage across 2. And that's actually going to be a little bit difficult to get to, but we can get there eventually. But we're going to use here a shortcut, I guess, to make this easier, which is noting that when two capacitors are in series like so, the charge on one will equal the charge on the other. Okay, and so that's this sort of in the same way that voltages of parallel branches like this are going to be the same. Same thing for this here. The charge across two capacitors in series will be the same. So we can actually rewrite this as Q2 is going to be equal to Q1 comma 2. And now we want to be thinking of this in terms of the combined or equivalent capacitor of C1 and C2, which means that we're now thinking about this instead. And this is going to make calculations much easier. At least it will save us a step, I should say. So let's maybe start with this right here. This shouldn't be too difficult to get. We have two capacitors here that are in series, and this is going to be similar to how we were calculating these in parallel. We have to do 1 over the equivalent capacitance, and that's going to be 1 over C1 plus 1 over C2. And then eventually what we'll get, well, actually, let me plug these in. But what we'll get here is that the equivalence capacitance is going to be 6 microfarads, like so. Okay, so we have one piece of information. Now let's get this one right here. This is actually also not going to be too difficult because what we have to keep in mind is that we found in the previous part that the voltage across this was 8.33 volts, right? And following Kirchhoff's rules, we start here with 10 volts, okay? So we're going with 10 volts, and then we pass through here, and it's going to be a voltage drop of 8.33, okay? And then we can pass through any of these branches, and it will be the same voltage drop, right? Because they're in parallel, which is to say, okay, let's pass through this one right here. So we can say minus V of 1 comma 2, and we'll be back at our start, which is to say we have to say this is equal to 0. So you'll be able to very quickly see that V1 comma 2 is just going to be equal to 1.67 volts. And this, again, should make sense. The voltage drop across every resistor here, or every set of capacitors, and also these resistors here, is going to be 1.67 because they're all in parallel. So now we have our two pieces of information. Our Q2 is going to be, going back to this, that Q2 is equal to Q1 comma 2. We can say that Q2 is going to be equal to 6 microfarads times 1.67 volts. And then what you should get from this is that Q2 is going to equal to 1 times 10 to the negative 5 coulombs, which I believe that would be 10 microcoulombs. Yes. And so that should be your final answer. Part C and part 2 of part C is now asking us, is the charge stored on capacitor C3 greater than, less than, or equal to the charge stored on capacitor C2? Okay, so we're now asking about comparing this to our previous answer that we got for Q2, or the charge of capacitor 2 here. And so what we need, this is going to be the most important formula here, is this. We're going to apply it to both. So that's to say that Q3 is going to equal to C3 times V3, and Q2 is equal to C2 comma V2. Okay, but then we also figured out that since Q2 is equal to Q1 comma 2, and that's just a property of capacitors in series, we can say that Q2 is equal to C1 comma 2 times V1 comma 2. But this branch here, this combined capacitance, is going to be in parallel to this one here, which is to say that they actually have the same voltage. So let's maybe we could just say that Q3 then is given by C3 times V1 comma 2. I could also just choose to replace this with V3. Either way, I just want to show that they have the same voltage here. So really, the only thing that we're now comparing is the capacitance. And so C3 here is equal to 20 microfarads, and C1 comma 2 is equal to 6 microfarads, and we got that from the previous problem. So since C3 is greater than C1 comma 2, we can also safely say then that Q3 must be greater than Q of 1 comma 2, which is to say Q2. And so we'd put here greater than, and for my justification, I would basically explain this calculation here that I just did, but in words instead. Part D was actually the freebie to this question, at least the first part was. We're asked that since now that the switch S is opened, determine the current through R1 immediately after it is opened. Well, immediately after it is opened, which is actually how the diagram is already, R1 is not even part of the circuit. There's not a closed loop that goes through R1. So there's going to be no current going through R1. And so this is a very, very quick answer here, which is that the current is going to be equal to 0. Part 2 of part D is definitely not as easy as the first one, but we can still get to the answer actually pretty quickly, okay? So calculate the current through R2 immediately after the switch is opened. So we're looking for I2, and that's going to be given by, well, V2 over R2, right? This is just Ohm's law. And well, we know R2. Do we know V2? Actually, we do. Yes, we do. And why is that? It's because we know that the voltage across these is 1.67. Right? And we got this from our previous answer, from our previous answers from up here. The voltage across them must be 1.67, and we know that also from this formula here, that this must hold true even when we open the switch. Okay, and so we can simplify basically our circuit here. Let's simplify this to only have one capacitor, one equivalent capacitor, which will still have a voltage here of 1.67, keep in mind, because we're just combining them that are in parallel. And let's just keep these two resistors like this. It doesn't really matter that we keep them separate, because what we'll know is that the voltage across R2 will be the same as the voltage across R3. Again, it must be because they're in parallel. And so we can say 1.67 minus the voltage across R2 is going to equal 0, because we can just form a loop using Kirchhoff's rules here, like so. And once we do that, that becomes pretty easy. That just tells us that V2 is equal to 1.67. So now our formula here just becomes 1.67 over 30 ohms. And then what you'll get is that the current is going to be 0.0557 amps. That's our final answer. Part E, we're told on the axis below, sketch a graph of the potential difference V across capacitor C2 as a function of time if switch S is opened at time t is equal to 0. And we're also asked to label the maximum value. Well, what we should know is that if we have a capacitor here that was originally charged, right, because we're at times equal to 0, and this was after the circuit when it was originally closed reached equilibrium, so it's the same point there, then we have charge here on our capacitor, which means that our voltage is going to definitely not be 0. It's going to be some positive number. And then what we also should know is that discharging capacitors will have their voltage decay exponentially like this, and it will sort of go through an asymptote here, never touching 0 technically, but it is discharging like so in an exponential fashion like this. So it should look like that concave up curve. And so we need to figure out what this Vmax is, and that's actually going to be the difficult part here. Uh, well, I say difficult, but actually we sort of already know some of this information. So for example, we're trying to basically get V2, which is going to equal to Q2 over C2. But keep in mind, we've already said before that two capacitors, actually it doesn't even really matter that they are capacitors that are in series. We've actually already calculated Q2, have we not? If we scroll all the way up here to part C1, we see here that we calculated that Q2 is equal to 1 times 10 to the negative 5 coulombs. Okay, so this is 1 times 10 to the negative 5. And we still know that C2 is going to be 15 microfarads, like so. So really, if we get this answer, we can get this answer as well, uh, because nothing has changed since we calculated this from part C1. This was like when the circuit had reached steady state, as you can see here, which, as we've said, is actually the same sort of system that we're talking about right now, except that we've closed the switch, but the charge on the capacitor will stay the same. So when you calculate this, what you'll get is 0.67 amps, or 667 if you want to write with that many digits like so. Or sorry, not amps. I'm messing this up here. Should be volts. And so that's going to be the voltage across this capacitor C2. So that's what we would want to write, 0.67 right here. If you didn't get the part C1 correctly, but you used the correct value when you're plugging in here, you should still get the right points. Capacitor C3 is replaced by two 10 microfarad capacitors connected in series. Switch S is closed and the circuit reaches equilibrium. Switch S is then opened at times equal to 0. All this is really saying is that they basically reran the experiment, but instead they had two 10 microfarad capacitors here instead of the 20 microfarad capacitor that they had here. So just imagine basically the same thing, but without that 20 microfarad, but instead 10 microfarad capacitors right there. So then part F asks us, for t is greater than 0, would the sketch of the graph of the new voltage across C2 as a function of time be above, below, or the same as the sketch for part E? And so this is what we drew for part E. Would it change given by changing the capacitors there? No, it would not, and let me explain why. You might be first thinking that, oh, two 10 microfarad capacitors in series, then that means that their overall capacitance will be equal to 20 microfarads. No, this is not true, and this is a mistake that I made myself on the exam, I'm now noticing, because you're thinking about two resistors in series, you can add their resistances, but two capacitors in series, you have to do the 1 over CEQ is going to be equal to 1 over C1 plus 1 over C2. And so we'd get is actually, I'm assuming, 5 microfarads for the equivalent capacitance. But even then, this will not impact our answer. And why is that? Because when we were originally figuring out what the voltage across this is, because we used the voltage across this to then be able to figure out what the charge must be across, or sorry, the charge must be across this, which is really the same thing as saying the charge across this. And then from there, we can also figure out the voltage across just that capacitor right there. None of that actually involved the capacitance that was happening right here. All that it involved was this resistor right here. And so let me scroll up and show you exactly that process there. We were able to get the voltage across R1 here, uh, but it really did not matter what was going through C1, C2, or C3. Okay, all that, or sorry, not what it was happening with C3. What really mattered here was going on through C1 and C2 when we were trying to figure out the voltage of that specifically. So when we got here the charge, and then we got here the voltage as well for that. So really nothing will change, and the explanation that I guess I would give if I could go back in time and change my answer would be saying something that the voltage across C2 is not dependent on the capacitance uh, of that branch of capacitors because they are in parallel. So no matter what, they'll have the same voltage. And then we can calculate the voltage of C2. It's not dependent on those capacitors. It's at most going to be dependent on this capacitor right here, what the voltage of this one will be. Okay, so yes, that will be FRQ number one. It was a pretty difficult one in my opinion. I'm starting to notice I got a couple parts wrong for sure, uh, but hopefully I got these right now. And so let me know if you think that I'm wrong about any of this. Again, it was the most difficult FRQ, so maybe I made some errors in this video as well. I hope not, but let me know if I did, and I'll be releasing the videos to FRQ number 2 and number 3 soon. Thank you for watching.